Hello and welcome back to the HIL for Microgrids module. In the previous lessons, you learned about microgrids in Typhoon HIL software. In this lesson, you will see how microgrid components can be put into action by creating a simple microgrid. Your task in this lesson is to create the microgrid shown here. This simple microgrid consists of a PV power plant, a variable load, a battery ESS, and a grid. The parameters of each microgrid component are given here. You can use these values to parameterize the microgrid components. Now let's go to the schematic editor and start building this microgrid model. For this exercise, you will use generic microgrid components. The main advantages of generic components are ease of use, straightforward parametrization, self-tuning capability, a constantly growing feature set, and better defined functionality maps for integration of communication. To begin, use the model initialization script to define all parameters that are given in the problem definition. Define variables for the voltage levels and the frequency of the system. Set V'Prim to 2.4 kV, Sec to 0.4 kV, and F to 50 Hz. These are the basic parameters that all components will share. Now insert a grid generic component and grid UI component and connect them together. With these components inserted, you are ready to configure the grid component. As you can see, this component also has parameters for short circuit power and inductive power factor. Grid short circuit power is a function of the grid impedance value. The grid inductive power factor represents the power factor when the grid is short-circuited, and can be calculated using the reactance to resistance ratio, or X/R. Values for these parameters are given in the presentation slide we saw earlier. Let's add them in the model initialization function. With that, you have successfully parameterized the grid component. Do the same for the PV power plant generic, variable load generic, and battery ESS generic components. All of these components are going to be connected to the same bus. As you can see here, all model parameters have been defined in the model initialization script. The parameters from the model initialization script are propagated to the DER components. It is worth noting that most DER components have a Converter Extras tab. These parameters don't influence the power stage of the model, only the control embedded in the generic DER component. Stable operation of the converter can be achieved by adjusting this parameter. A transformer can optionally be included in all DER generic components. Let's compile and load the model and create a new SCADA panel. In the handout materials, you can find a widget library. This library consists of several predefined widgets for the DER generic components. This library will help you to create a SCADA panel within a few minutes. You can find more information about widget libraries in the tutorial linked in the Materials tab. Let's include this library. To do this, Add the path of the folder where the library is saved to your user library's path. Now you can update your library's path by clicking Apply and Save, then reload your libraries. At the bottom of the library dock, you will find the generic DER widgets library. To start, drag and drop the PV Power interface. You now need to link the widget to the model component. All predefined DER widgets are linked to dedicated UI components in the model. The PV Power interface subpanel has now been placed in the SCADA panel and linked to the appropriate DER. Fill out your panel by doing the same with the other interfaces. You now have a fully populated SCADA panel for your microgrid. Let's run the simulation. You can see that the grid component supplies the load with around 90 kilowatts of active power and around 108 kilovolt amperes reactive power. Try changing the active and reactive power set points of the load. You can change the power set points inside the load interface subpanel by modifying the entries in the active and reactive power text boxes. Set the active power to 1 per unit and reactive power to 0 per unit. You can see that the load is supplied with 450 kilowatts of active power, which is the nominal active power of the load. The load can be configured as none, quadratic, or Taylor series. Active and reactive power consumption can depend on voltage and frequency variation. You can find more information about load configuration in the documentation linked in the Materials tab. For this example, use a simple load without any dependencies. All of the subpanels can be configured to open in windowed mode. Open the subpanels this way. Now let's turn on the PV power plant. The MCB status LED is currently indicating that the inverter is in the disabled state. To enable the PV power plant, check the Enable checkbox. The LED is now indicating that the inverter is in the running state. You can see that the inverter is running and that the active and reactive power are limited to 0.2 per unit. Try increasing the limit of active power to 1 per unit. You can see how the active power rises to the new active power set point. The output power of the PV power plant is directly influenced by the irradiation and temperature values. Try moving the sliders for irradiation and temperature. You can see how active power changes in response to different irradiances and temperatures. Similar to the PV power plant, the battery ESS component has 4 LED indicators of the state. Run the battery ESS in grid following mode. As you can see, in grid following mode the inverter follows the active and reactive power references. The battery ESS can operate in 3 different operation modes: grid following, droop, and isochronous. The droop characteristic can be defined in real time using the frequency droop offset, frequency droop coefficient, and voltage droop coefficient. These parameters define the droop curve. There is also an option to enable grid codes in the battery ESS component. You can find more information about this in the tutorial video linked in the Materials tab. In this lesson, you learned how to create a simple microgrid model in 10 minutes. The only thing missing is the microgrid controller. In the next lesson, you will see a more functional microgrid that consists of more DER components and a microgrid controller model developed using the signal processing toolbox. Thank you for watching.